Area and lengths in polar coordinates. Let's start by reviewing the area of a sector. To find the area of a region in a polar coordinate system, we use sectors instead of rectangles. As a reminder, a sector is a part of a circle, and the area of a sector with central angle theta is given by, well, first we need theta over 2 pi, which represents the fraction that corresponds to that part of the entire circle. So we have, if theta is the central angle, then the fraction of the entire circle is theta out of 2 pi. And we take that fraction and multiply it times the area of an entire circle, which is pi r squared. So the area of that part of the circle, if we multiply these two, ends up looking like 1/2 r squared theta. So notice that the pi's cancel out. So 1/2 r squared theta is the area of a sector, provided we have the angle theta given in radians. Now let's move on to approximating area using sectors. For a curve r equals f of theta, the area of each approximating sector is given by a sub k equals 1/2 times r sub k squared delta theta. Let's look at this graph over here. We have our polar curve r equals f of theta, and we're interested in the area between the two angles. Let's say theta equals some alpha and theta equals beta. Here we're using 4 sectors to approximate the area. So we'll go ahead and say that the area of each sector is a sub 1, a sub 2, a sub 3, and a sub 4. And so each of those areas is found by using the area of a sector formula, where the radius of each sector is found by using that halfway radius here. So that's like my R1. And then delta theta is dividing this total angle by 4. So each of these has an equal angle measurement here. So similar to like how we have a delta x when we're talking about using rectangles to approximate area in functions in Cartesian coordinates in x and y. So we can see that there's this amount of error associated with using a finite number of sectors. But if we increase the number of sectors that we use, so here in this first picture we're using 4, and then now we're doubling it to 8 sectors, we can see that we have a better approximation with less error. So we have our Riemann sums that approximate the region. That's a finite number, an n number of sectors. And if we take the limit as n approaches infinity, so if we increase the number of sectors and head towards infinity, then we're going to get to an integral that finds the exact area that we are looking for between two angles given a polar curve. So here we're going to look at the formula for finding area using polar coordinates. The area of the region between the origin and r equals f of theta from theta equals alpha to theta equals beta is given by the integral from theta equals alpha to beta of 1/2 r squared d theta. And note, as you go from alpha to beta, the curve must be traversed exactly once. In this example, we want to shade the region enclosed by the cardioid r equals 2 times the quantity 1 plus cosine theta from theta equals 0 to theta equals pi, and find its area. So here the polar curve is graphed, and the region enclosed by the polar curve from theta to pi is going to be the part on the top of the x-axis. So we're looking at shading the region from theta equals 0 to theta equals pi. So theta equals 0 is on the positive x-axis, and then pi is on the negative x-axis. And so we are extending from 0 to pi, moving along our polar curve. So this is the region that we want to find the area of. And what we're going to do is use this area formula up here. So we're looking at A is equal to the integral from 0 to pi, and then we have 1/2 the radius. Well, the radius is given by the polar curve. R equals 2 times the quantity 1 plus cosine theta. So we have 2 times 1 plus cosine theta. All of that is going to get squared d theta. So this is the integral that I need to evaluate to find the area. So let's go ahead and simplify it a bit. So here we're going to go ahead and have 0 to pi of 1/2 times 4 times 1 plus cosine theta squared d theta. So the 2 gets squared and the 1 plus cosine theta gets squared. 1/2 times 4 is 2, and we can pull that 2 out to the front. So 2 times the integral from 0 to pi of 1 plus 2 cosine theta plus cosine squared theta d theta. So I'm distributing out 1 plus cosine theta times 1 plus cosine theta. The first two terms in the integrand have a general antiderivative, but cosine squared theta we'll need to use the power reducing formula on. So we have 2 times the integral from 0 to pi of 1 plus 2 cosine theta plus 1/2 plus 1/2 cosine of 2 theta d theta. Combining 1 and 1/2 as 3/2, we get to 2 times the integral from 0 to pi of 3/2 plus 2 cosine theta plus 1/2 cosine of 2 theta d theta. After making some room here now, I have 2 times 3/2 theta plus 2 sine theta. And then here I'm going to have 1/4 sine of 2 theta. So here, remember the inside 2 theta, we're going to have an extra 1/2 come out of that from the antiderivative. And then this is evaluated from 0 to pi. So let's go ahead and plug in pi. So we have 3/2 pi plus 2 sine of pi plus 1/4 sine of 2 pi minus, now thankfully if we plug 0 into each of these we are going to get 0. Sine of 0 is 0, so this is just minus 0 there. And in fact, sine of pi and sine of 2 pi, those are also 0. So what we really have left here, so this one is 0, this one is 0, we just have 2 times 3/2 pi, which is 3 pi. So before moving on, I just want to recap that what we've done here in finding this number of 3 pi, that represents the area between the angles 0 and pi and the polar curve and the pole. So starting at the angle 0, we are moving in a counterclockwise direction, collecting area in the form of sectors. So we're going in this counterclockwise direction, and we're collecting, of course, these really, really thin sectors as I move around and head from that starting angle of 0 to this angle of pi. In this next example, we'll just set up the integral needed to find the area of the shaded region. With the given polar curve, r equals the square root of theta. So we can see this looks like a bit of a spiral, but we're only being asked to find the area of the shaded region, and that's the part here that's on the left side of the y-axis. So we need to figure out what angles to use for our area formula. So the area extends from theta is equal to pi over 2, and then we're going all the way around down here to this angle of 3 pi over 2. So we're going to go ahead now and set up our area formula as the integral from pi over 2 to 3 pi over 2 of 1/2 times my radius, but that is my polar curve, r equals radical theta, so we have radical theta squared d theta. And so we'll actually just clean this up a little bit. We can pull the 1/2 to the front, and then on this one, the square root of theta squared is just theta. So a pretty simple integral. But once again, before moving on, I want to reiterate how we are collecting area. So we're starting at this angle of pi over 2, and we're collecting the area of these very thin sectors as I move around in that counterclockwise direction until I get to 3 pi over 2. In this example, I want to set up an integral needed to find the area inside one petal of the rose curve r equals 4 sine of 3 theta. So this rose curve has 3 petals. We want to find the area inside of one petal. So here, let's say we want to find the area of the petal that's over here in quadrant 1. Well, we need to be precise about our limits of integration here. Where does this polar curve extend from? From what angle to what angle? So we need to look for this angle here, which kind of looks like theta equals 0. But then we also need to find this other angle here. And we're kind of unsure what that value is. So theta equals, I don't know. So what we have to do is find what are called the polar zeros. I have to figure out what angle takes me back to the pole, to the origin. So to do that, I'm going to need to set my curve equal to 0. So I need to solve, when does 4 sine of 3 theta equal 0? So I can divide both sides by 4. I have sine of 3 theta is equal to 0. So how do I solve this type of trig equation? Well, let's just think about what angles do I plug into sine to get out 0. So in other words, maybe think about this problem for a second as sine of some x value equals 0. Instead of 3 theta, let's just make it x for a second. What angles do I plug in to get out 0? Whoops. All right, well, 0 is one of them, so x would be equal to 0. Also pi, and then 2 pi, 3 pi, and so on. Also, the negative multiples of pi. So negative pi, negative 2 pi, negative 3 pi, and so on. So we'll just stick with maybe this list for now. But again, the problem wasn't solve sine x equals 0. It was solve sine 3 theta equals 0. So what we can do is replace this x with 3 theta. So 3 theta is equal to 0 pi, 2 pi, 3 pi, and so on. And then we can solve for theta. So ultimately we want to solve for theta. So we'll divide both sides by 3, divide all of these answers by 3. So we end up with theta is equal to 0, pi over 3, and then 2 pi over 3, and pi, and then there are a lot more answers here. So what we did though was we found the polar zeros. What angles do I plug in to this polar curve that send me back to the origin? Well, 0 is one of them, and it looked like 0 was one of them, but now we can see this other angle here is theta equals pi over 3. And we found some more values, right? 2 pi over 3 and pi. So what those are these angles over here that trap the next petal in. So this is 2 pi over 3, and then the next one extends to theta equals pi, right? And then there are more answers, and that would be what finds the bounds of the next petal. So we have enough though. I mean, we have what we were trying to find, these limits of integration for our area formula. So let's go ahead and set up the integral. So our area is going to be the integral from 0 to pi over 3 of 1/2 times r squared, so 4 sine of 3 theta squared d theta. And so we can kind of clean this up a little bit. The 4 would get squared, that's 16. 16 times 1/2 is 8. We can pull the 8 to the front. So 8, the integral from 0 to pi over 3, and then we'd have sine squared 3 theta d theta. And the integration on that would require the power reducing formula. In this example, I want to set up the integral or integrals needed to find the area of the region that lies inside the circle r equals 1 and outside the cardioid r equals 1 minus cosine theta. Let's start by shading the region we're trying to find the area of. We want to be inside the circle r equals 1. That's the circle centered at the origin with radius 1, so I want to be inside that circle. but I want to be outside of the cardioid. So I want to be the region that's outside of this cardioid. So I'm going to need to erase part of this circle. So I don't want any part that's inside the cardioid. So this region here is what I want to find the area of. All right, so let's go ahead and get started thinking about this one. So we're going to go ahead and set up two integrals here. So first, I'm going to find the area of the semicircle between negative pi over 2 and pi over 2. So down here is negative pi over 2, and up here is pi over 2. So first I'm going to find the area of the semicircle here. So the right side of the circle of radius 1, so that's extending like from negative pi over 2 to pi over 2. We're thinking about essentially cutting it up into sectors like this. So we can find that actually using just the half of the area formula for a circle of radius 1, but I'm going to choose to set it up as an integral. So the first integral I'm going to set up here is the integral from negative pi over 2 to pi over 2 of 1/2 times the radius, well the radius is just 1, the radius squared d theta. So again, that's finding the area of that semicircle, the right side of this unit circle, but then I need to carve out, or I need to take away a portion of that. So I'm going to need to take away this little region here. And so the way that's going to be found is I'm going to subtract another integral. I'm going to subtract the integral from, again, negative pi over 2 to pi over 2. So I'm starting from down here and collecting those little sectors. Negative pi over 2 to pi over 2 of 1/2 the radius of the cardioid, 1 minus cosine theta squared d theta. So again, the first integral finds the area of the full semicircle, and then the second one carves out these two little pieces here. Now, since these do have the same limits of integration, we can go ahead and combine them together to be one integral. So we can say negative pi over 2 to pi over 2 of the first integrand, so 1/2, and that's really it, because times 1 squared, it's just 1/2, and then minus 1/2, 1 minus cosine theta squared d theta. And I can factor a 1/2 out of both of these if I want. So we're looking at 1/2 the integral from negative pi over 2 to pi over 2 of 1 minus the quantity 1 minus cosine theta squared d theta. So that's the setup of the integral, or one way to express it, because what you might have also been thinking is there's some symmetry involved in this problem. So another way that we could have done it, another option, so I'll come down here and put or, what we could have done was found just the area in quadrant 1, so from 0 to pi over 2, and then doubled it. So it's still going to have this same integrand here, but the limits of integration are going to change. They're going to go from 0 to pi over 2 of that 1 minus cosine theta, all as a quantity squared d theta. But what's happening is we're going to double that. So it's going to be 2 times that 1/2 in front. And so, of course, the 2 times 1/2 cancels. So we can just find the integral from 0 to pi over 2 of that same integrand as before, and that's going to find the same area because we're able to use symmetry. In this last area example, we're going to set up the integrals needed to find the area of the region shared by the circles r equals 1 and r equals 2 sine theta. So coming over here to the diagram, we have this orange circle is the r equals 2 sine theta polar equation, and the blue circle is r equals 1. So that's the circle centered at the origin with radius 1. So we're trying to find the area shared by the circles, or the area that basically looks like a little eyeball. It's this region of overlap here. So in order to find this area, let's think about starting at the angle 0. So if we think about starting at 0 and then moving in a counterclockwise direction to start collecting area, the first function we're going to be collecting our area from is the orange circle, r equals 2 sine theta. So if we kind of think about collecting these little sectors, so first we are on the orange function, r equals 2 sine theta, right up until this point of intersection here. So we are going to need to find that point of intersection. So let's start our problem here. So our problem is going to look like the integral from 0 to, well, whatever this angle point of intersection is. But then we're going to have 1/2 the function 2 sine theta squared d theta. So that's going to find the area of this little portion right here that I've started to sort of sketch out. But again, I need this point of intersection, this angle. So to find that, we're going to have to set the two functions equal to each other. When does 2 sine theta equal 1? Well, I'll divide by 2 and instead think about when does sine theta equal 1/2? And so between 0 and 2 pi, when does sine theta equal 1/2? Well, that's pi over 6 and 5 pi over 6. And basically that checks out with our graph. We can see this looks like about pi over 6 here, and then there's this other point of intersection here, and that one is 5 pi over 6. So we have our missing limit of integration over here for this first integral. That's going to be pi over 6. So this first integral is going to find this little tiny area right here, but then I have to keep going, and now as I continue on past pi over 6, the area I'm going to be collecting is on the function r equals 1. So I can kind of keep going, and you know what? I'm actually going to stop at the angle pi over 2. So I'm going to go ahead and set up an integral that finds the rest of this little area here from pi over 6 to pi over 2. So we're going to have plus the integral from pi over 6 to pi over 2 of 1/2. Our r value this time is just 1, so 1 squared d theta. Now, why did I stop right there? Well, because I recognize that there's symmetry. So these two integrals are going to find half of the area I'm looking for, sort of half of this eyeball shape. And so what I can do is just go ahead and double this. So I can go ahead and I'm just going to sneak a 2 in front of both of these pieces here. So now these two integrals will find the area shared by these two circles. Now let's switch gears and talk about arc length of a polar curve. From the arc length formula for parametric equations and the fact that x is equal to r cosine theta and y is equal to r sine theta, we get the arc length for a polar curve, r equals f of theta, as theta goes from alpha to beta as the following. So the integral from theta equals alpha to theta equals beta of the square root of the quantity r squared plus dr d theta squared d theta. And again, as we go from alpha to beta, the curve must be traversed exactly once. Let's jump into an example. Let's find the length of the curve r equals the square root of 1 plus sine 2 theta, where theta is between 0 and pi times radical 2. So we have our arc length formula. It's really just a matter of substituting in, and then we are going to start to practice our integration since we just did a lot of setup earlier. So here, we know we're going to have to find dr d theta, so let's just go ahead and do that now. So dr d theta, the derivative of r with respect to theta, will require the chain rule here, because this is 1 plus sine of 2 theta all to the 1/2. So we're looking at 1/2, 1 plus sine of 2 theta to the negative 1/2 times the derivative of the inside. So we're looking at the chain rule here. The derivative of 1 plus sine 2 theta, that's going to be cosine of 2 theta times 2. So there's really a double chain rule happening there. So the 1/2 and the 2 simplify to 1. So I'm going to write this as cosine 2 theta over the square root of 1 plus sine of 2 theta simplified. All right, so that's dr d theta that we're going to have to substitute in. We have r that we're going to have to substitute in, and then our alpha and beta are these angles here. So let's start writing things out here. Our length is going to be the integral from 0 to pi times rad 2 of the square root of, we're going to do r squared, so the square root of 1 plus sine of 2 theta squared, plus our dr d theta, so that's cosine 2 theta over the square root of 1 plus sine of 2 theta. All of that is squared, and underneath the square root, d theta. All right, so some nice things start to happen. The square root and the squared are going to cancel out there, and let's start to write out what we're going to have. The integral from 0 to pi times radical 2 of the square root of, we're going to have 1 plus sine of 2 theta, plus, now here, cosine 2 theta gets squared, so we'll write that as cosine squared 2 theta. And then here, the square root and the square cancel, so we have 1 plus sine 2 theta in the denominator. So let's try to make these have common denominators here. So we're looking at the integral from 0 to pi times rad 2 of the square root of, we're going to have a big fraction bar in here. We're going to have that common denominator be 1 plus sine 2 theta. So we're going to have to multiply this side over here on the top and bottom. So like this is over 1. So we'll multiply the top and bottom by a 1 plus sine of 2 theta. So that's going to be 1 plus sine of 2 theta times 1 plus sine of 2 theta plus that cosine squared 2 theta on the top. Gonna need some more space. All right, we have some more space. We have 0, pi times radical 2, square root of. In the numerator, we're gonna have to distribute these two binomials out. That's gonna leave us with 1 plus 2 sine of 2 theta plus sine squared 2 theta plus cosine squared 2 theta all over 1 plus sine of 2 theta d theta. We have an identity in there. We have sine squared 2 theta plus cosine squared 2 theta. That is 1. That's the Pythagorean identity there. So this portion here, right, is just 1. And so 1 plus this 1 in the front is 2. So our next line is going to be the square root of 2 plus 2 sine 2 theta over 1 plus sine 2 theta. Nice things are starting to happen, or will happen shortly. So here we can pull a 2 out of the numerator. Make some more space. So I have 2 times 1 plus sine of 2 theta, and then there's a 1 plus sine of 2 theta on the bottom. Look at that, those cancel, and I'm really just integrating rad 2. So 0 to pi times rad 2. The integrand is just a number, rad 2. We're integrating with respect to theta, so it's going to be radical 2 theta evaluated from 0 to pi times rad 2. We'll plug in that pi times rad 2. If we plug in 0, we get 0. Rad 2 times rad 2 is 2. All that work, and we end up with 2 pi. And in this example, we're going to find the length of the cardioid, r equals 1 minus cosine theta. So here, although the limits of integration aren't explicitly provided, in order to get the length of the full cardioid, which is like that heart shape, we're going to have to go around the entire unit circle. So we're going to have to extend from 0 to 2 pi. So to set up our arc length here, we're going to say the integral is from 0 to 2 pi of the square root of r squared, so 1 minus cosine theta squared, plus dr d theta squared. So let's take that derivative over here. Dr d theta, well, the derivative of cosine is negative sine. There's already a negative there, so just sine theta. So inside here, we're going to have sine squared theta d theta. All right, so let's go ahead and distribute out 1 minus cosine theta squared. So that's going to give us 1 minus 2 cosine theta plus cosine squared theta. Remember that we can't just distribute the exponent. That doesn't work, so I'm distributing out the binomials here. And then plus that sine squared theta d theta. So we have that identity again. Sine squared theta plus cosine squared theta is 1. So all of this right here is a 1. So what I have underneath the radical is going to be radical 2 minus 2 cosine theta d theta. And right here, we might feel a little bit stuck. So how do I go about integrating this? Well, ideally, I would like some quantity squared underneath a square root. That would be ideal, so that the square root and the squared cancel. All right, had to make some more space here. So let's actually factor the 2 that's underneath the radical in both terms here. So I'm at a place where I can say 0 to 2 pi, the square root of 2 times the quantity 1 minus cosine theta d theta. And I can actually even pull out the radical 2 there. And so I can make this like radical 2, the integral from 0 to 2 pi of the square root of 1 minus cosine theta, and then d theta. So now, again, we're trying to get the part under the radical to be a perfect square somehow. And we're basically going to use the power reducing formula in reverse. So let's remind ourselves of the power reducing formula for sine. So sine squared x is equal to 1 minus cosine of 2x over 2. So I have 1 minus cosine theta. So it's similar, but not quite the same thing. So here's what I'm going to do. I'm going to multiply the 2 to the other side here. So I know this equation is true. So whatever I do to one side, I can do to the other. So how about I multiply by 2, so I know 2 sine squared x is equal to 1 minus cosine of 2x. Okay, I'm getting closer. This right-hand side, 1 minus cosine 2x, I need it to be 1 minus cosine theta. So what we're going to do is a little bit of a substitution. So we're going to let this x be theta over 2. So right here, I'm going to make a substitution. Let's let x be theta over 2. If this is truly an equation, I should be able to substitute x into both sides of the equation, and it will still hold true. So let's replace x with theta over 2. So we're going to have 2 sine squared of theta over 2 is equal to 1 minus cosine of 2 times theta over 2. So the 2 over 2 cancels, and my right-hand side is 1 minus cosine of theta. That's exactly what I have underneath my radical here. And what I just showed that was equal to is 2 sine squared of theta over 2. So now I can go ahead and replace 1 minus cosine theta with 2 sine squared of theta over 2. So here's where I'm at. I have this radical 2 in the front, the integral of 0 to 2 pi of the square root of 2 sine squared theta over 2 d theta. And so now these are multiplied, right? So I can pull out another radical 2, copy it to the front. So I'd have just a 2 in the front, the integral from 0 to 2 pi, and then the idea is that the square root and the squared are going to cancel. So now I'm just integrating sine of theta over 2 d theta. And this has a general antiderivative. So here, let's take the general antiderivative. Let's make a little bit more space. So we'll leave the 2 in the front. The antiderivative of sine is negative cosine. So we're going to have negative cosine of theta over 2, but we're going to have to put the reciprocal of 1/2 in the front. So we're going to have an extra 2 in the front there, right? Because basically the chain rule would pop a 1/2 to the front, so I need a 2 in the front to cancel that. What's really happening is a U substitution, but we want to be able to sort of do that one in our head. And so then we're evaluating this from 0 to 2 pi. So we have -4 cosine of 2 pi over 2 minus -4 cosine of 0 over 2. And so -4 cosine of pi plus 4 cosine of 0, a little bit more space. So we have -4 cosine of pi is -1 plus 4 times 1. So we have 4 plus 4. So we get out 8. So the length of that curve given in polar is 8.